This is the video solution to one of the example problems where we're going to find the net electric field at a point in space. The task here is to calculate the net electric field at a point in space as shown below. So I've got a particle on the left that's blue with a net charge equal to 5 protons. I have a particle on the right that's red with a net charge equal to 4 electrons. And I can see the distances that are separated by 3 nanometers, 2 nanometers, and 2 nanometers to the point. Now nanometers, that's 10 to the negative 9 when you start doing the math. Alright, so I want to look at this. First thing I need a little more geometry to figure out some distances and some angles. So I'm going to draw a line between the point and the point in space and the particle on the left. And then I'm going to draw, then I'm going to calculate the length of this line using the Pythagorean theorem. And you can see I get square root of 13 times 10 to the 9th. And that's the length of the line from the blue point over to the point in space. Now I need to find the angle in the upper left-hand corner of this triangle. So I'll use the tangent function. Tangent is opposite over adjacent, so it's going to be 2 meters divided by 3 meters, or nanometers actually. So theta is equal to 33.69 degrees, and that's the angle in the top left. Now I need to do some of the same geometry for the red particle. So I'll draw my line from the red particle to the point in space, use Pythagorean's theorem to get square root of 8 times 10 to the negative 9. So that's the length between the particle and the point in space, and I need to find the angle. So tangent theta is rise over run, which is basically inverse tangent of 1, and that's 45 degrees. So that's the angle in the top right-hand corner. Alright, to start solving this, what I need to do is focus on one of the particles and the point in space. So I'm going to focus on the blue particle and the point in space. I'm going to keep in mind the other particles, but I'm not going to see how they interfere with each other. So just one particle at a time and the point in space. Alright, with the shown, first thing I need to do is figure out what the electric field is going to do. So the electric field is defined as a path a positive particle would take. So I'll put an imaginary positive particle there, and I'll see how it would react to this positive particle. And it would be repelled in the direction just shown. So that means that the electric field, due to that 5 proton charge, is going to go down and to the right. And it's going to have components that are horizontal and vertical. And the angle in the top left-hand corner is the same angle because these are similar triangles. Now I need to find the magnitude of the electric field with that 5 proton charge. So this is where my formula comes in. Notice, well, in this case you really can't tell, but I'm not keeping any of the signs when I'm doing the math on this. So I've got 5 times the number of the charge of a proton, that's the 1.602 times 10 to the negative 19 coulombs. And now that's times coulombs constant divided by the distance squared. And when I do that, I get 553.922 newtons per coulomb. So that's the length of the red line. Now I need to find the length of those components, the horizontal and vertical components, because that's what I'm going to add up. So the horizontal component is 553.92 newtons per coulomb cosine, and that gives me 460.89 newtons per coulomb. Vertically, it's 553.92 newtons per coulomb sine 33.69, and that's going to give me the 307.26 newtons per coulomb. So great, now I've got horizontal and vertical components, and that's what I'm going to add up, just like I did with free body diagrams. I want to add up my vectors here using electric fields. Alright, so now let's neaten up the page a little bit, get rid of some of the clutter so I can keep going. And I'll take my triangle just to, again, get rid of the clutter, and I'm going to slide it to the right a little bit here. So there it's to the right. Now it's time to focus on the red particle. So the blue particle goes away, and I'm going to look at the red particle and the point in space. Now I've got to figure out what its electric field does, so I'll do my imaginary positive test charge, and that'll be attracted towards the red particle, so that tells me the electric field is going to go towards the red particle this time. So that's the electric field due to the particle with the 4 electron charge, and it's going to have horizontal and vertical components to it. And there's my 45 degrees. Next I need to find the magnitude of this red line, the electric field. So I'll use my formula, electric field is equal to kq over r squared, putting in 4 times the charge of an electron. I'm just interested in the magnitude, because all this formula is going to do is tell me how big the electric field is. The direction is determined the way I did in the very beginning by seeing how that imaginary blue positive test charge would travel. So this just calculates the magnitude, that's why I'm dropping the negative sign. Do all my math, and I get 720.10 newtons per coulomb, and that's the hypotenuse in that triangle. Now to find the horizontal side, that's 720.10 times cosine 45, 509.19 newtons per coulomb, and vertically it's going to be 710 sine 45, and it's going to be the same answer, 509.19 newtons per coulomb. Let me neaten this up a little bit, get rid of some of the clutter. And now what I'm going to do is I'm going to move my little point in space, so I'll show you where it really acts, and that's over here. So these two vectors, the two E fields, due to the 5 particle charge and then 4 electron charge acting on that point in space, I've just slid everything kind of off to the side of the screen so I can get some room to do a little bit of typing. Alright, so the net electric field in the x direction, I add up the x components. They're going the same direction to the right, so I'll make them both positive, and that gives me 970 newtons per coulomb. The net electric field in the vertical direction, well, one's going up and one's going down, so I'm going to call the one going up positive and the one going down negative. That's why where the negative came from in that formula of negative 307.26. Add those and I get 202 newtons per coulomb. So now I'm ready to actually find the answer. So I'll make a solutions triangle using these two as my components to the solutions triangle. So I'll have a horizontal component and a vertical component. Since EX is positive and EY is positive, I know that the X goes in my positive direction and the Y goes in my assumed positive direction. If the answer came out negative for either one of those, then I'd flip my arrow and put it in the negative direction. But these are both positive. So now they both can go over and up. And what I'm looking for is the hypotenuse of this triangle, which is the answer to the question. That'll be the net electric field and the angle. So there's the vertical, and there's the horizontal. That's where the numbers are going to come from. I'll use Pythagorean's theorem to find the net electric field, 991 newtons per coulomb. And then I'll use the tangent functions, opposite over adjacent, to give me the angle is 11.8 degrees. So these two numbers make up the answer. It says calculate the net electric field of the point in space below. The electric field is 991 newtons per coulomb, and it's 11.8 degrees in the first quadrant.